So in Chapter 9 of Matter and Interactions, they ask you to think about having two spheres, in principle two atoms, connected by a spring, the spring representing the bond between the atoms. And they want you to think about a few types of energy. They want you to think about the energy of the vibration between the two atoms. They want you to think about the translation of the two atoms. They want you to think about their rotation about the center of mass. Basically, they use this as a model to help you think about the different kinds of energy that can occur or be stored, for you British listeners, in the molecule here. And so I thought it would be neat to take a look at a code that models this little molecule here. So basically we've got a simple molecule of two atoms and a bond between them. One of them is green and one is red, so we're going to call them green and red just to keep track of them. And then we have a spring going between them. Now this is a simple model with just two. You could add a third one, which would get interesting. Like you got a blue one that's connected to the green, or you could have the blue one connected to both the red and the green, and maybe they have different spring stiffnesses between them. That's all really interesting, but the essential physics is contained in just the two particle model. And so we set up all the necessary information for them. We give each of them a mass. We're going to give them identical masses for now. You can see what happens when you make the masses different later. And then we give each of them a momentum. Now I'm not giving them the same initial momentum. Initially, the red atom is stationary, and then the green atom is moving to the right a little bit. You can see that here, that basically the molecule as a whole is rotating, and it's rotating about the red one. And then of course it's gonna start to rotate about the center of mass, but initially it looks like it's pivoting around the red for those first couple frames. And then we need to give the stiffness of the spring between them. So this is just the strength of that bond. So the higher you make this, the tighter that bond is, and the lower you make this, the weaker the bond is. And then we need to give the spring an unstretched length. So right now the unstretched length, or L0, is 0.9. So that's 90% of the original distance between them, because their original distance is going from y equals 4 to y equals 5. So it's stretched a little bit. It's stretched a teeny bit compared to the unstretched length. And then of course these things are falling because I've added in a uniform gravitational field. You could turn this off if you wanted them to be in space. Then we move down here to the animation loop. I've set it up to run as long as the green one is inside of the grid, so that's why you see the red one pop out here. You could also add additional ands here. You could add additional conditions for it to check the red one's position. I don't think it's going to make that big a difference unless you have these things, stretching out by miles and miles. I don't think that's going to make a huge difference. Then we move into the loop. I'm sure I don't need to review the Euler-Kromer method with you, but just for your edification, we first need to calculate the force on each of these atoms. So we give each of them a weight. So here's the mass times the gravitational field times down vector. Here's the mass times the gravitational field times the down vector. And then we need to give them the spring force. Usually I split this up into several lines, but by this point in a matter and interactions course, you've probably seen the spring force calculated by now, so you can probably handle it in a single line. Basically, we're keeping track of the distance between them using the spring's axis variable. So this vector here, the spring dot axis, gives you the separation distance between the two, but also the vector that goes between the two. So you can think of this as the magnitude and direction of the atom to atom distance. And so basically we set it up as the spring stiffness. Let's try that again. So we set it up as the spring stiffness here times the amount that the spring has been stretched by. Remember, it's not the distance between the two, it's the amount that the spring has been stretched by. So we're just taking the magnitude of the spring's current length minus the spring's natural length. And that order is important because if this is bigger than this, we get the force going in one direction. But if L0 is bigger than the spring length, then we get a force in the other direction. Basically, this is set up so that the spring always moves back toward equilibrium. If you were to reverse this, the molecule here would explode. We don't see any molecules exploding like that, so we assume that the spring force works like this. And then we need to turn this thing into a vector for it to be a proper force, and so we just use the hat function here to get the unit vector of this spring dot axis. And then of course there's a minus sign out in front so that we're always moving back toward equilibrium. Again, if you remove that, the molecule explodes. And then to get the spring force on the green atom, it's really easy because that's going to be the negative of the red atom's spring force. This is Newton's third law at work. Whatever force red exerts on green is the negative of the force that green exerts on red. And so then if you wanted to add other forces, like say you wanted to add a damping force, you could calculate that here. And then basically here we just add up all the forces. So if you were to add a damping force, you would just say plus green dot damping plus red dot damping here. And then we move along with the Euler-Kromer method. We update the momentum. Again, momentum changes by the force times dt. And then we update the velocity. That's going to change by, that's going to be set to the momentum divided by the mass. And then we update the positions. So that gets increased or decreased by the velocity times dt. And then down here we need to update the information about the spring. So we have the spring always starting out at the green and then always heading from the green to the red. That's what this little vector subtraction does here. And actually I made a note to myself, there's no physics here, just visuals, but actually that does contain the physics because we're using the spring axis back up here. So I need to delete that for honesty's sake. And then we of course just update the time for when we need that. And so basically you can change the initial conditions of this, their initial position and momentum, to get whatever kind of animation you want to kind of study how this molecule behaves. And to assist you in your study, what I thought we could do with this video would be to create a graph for the different energies that are going on here. Matter and Interactions wants you to study this molecule as a part of a unit on energy, and so I thought it might be helpful if we took a look at the energy. So let's start out with a graph. Let's give it an x title of time, because time is going to be our independent variable along the horizontal axis. And our y title is going to be energy. That's going to be the dependent variable along the vertical axis. And let's see, then we need to create a few different G curves, graphical curves. So let's start with the kinetic energy. So let's start with K green graph. That's going to be a G curve. And we'll give that color equals color dot green, since that is the color of the object we're looking at. Comma, then let's give this thing a label of green kinetic energy. There we go. And then we'll do the same thing for the red. Copy and paste. Have this one be the red. Make this green into a red. Make this green into a red. Awesome. So those are the two kinetic energies we'll be working with. Why don't we go ahead and calculate those down here, just to make sure that our graph's working out the way we think it will. Let's see here. Let's do this. Let's have this be, calculate energies. And so we'll have red K. Actually, this is probably seeming pedantic, but let me make these little k's and a capital K's, just so we don't get it confused with the spring stiffness Ks up here. So the red kinetic energy, let's see, energy is 1/2 times, we're going with red, so we'll go red dot mass times magnitude of red dot velocity squared. So good old 1/2 mv squared. And again, you have to take the magnitude of the vector. VPython does not like it when you square a vector, so you have to take its magnitude and then square it, which is what you're really doing mathematically. Then we'll do copy paste, change the reds, into greens. Paste, paste. There we go. All right, and that ought to be enough to get us our kinetic energy graphs. So now as these things float around, oh, right, I need to actually add the dot plot, don't I? You know, I love how I warn my students about these mistakes because I make them all the time in my own work. Dot plot. So we'll need to have time, comma, green K. I guess I flipped the order here. That doesn't really matter. We'll do copy. Actually, you know what? That's going to bug me if I leave those out of order. There we go. Then we'll make this one the red one. Red, green, turn into red. There we go. All right, let's try that again. Ah, there we go. Just took a second to start. Okay, cool. So we see the kinetic energies are changing. So the green one's slowing down while the red one is speeding up. I can see that here. The red one's definitely swooshing around this way, but then the red one slows down, and now the green one is swooshing down around this way. There are a couple of brief instances in which they have the same kinetic energy. Yeah, that's pretty cool. Okay. Wow, that's a neat graph. I love it when you do studies like this and you get out a graph that's not a typical function. You know, this is not a sine or cosine. I mean, this is what nature does. You know, sometimes nature is nice and gives you a sine or cosine, but a lot of times nature just gives you something bumpy and wiggly like this, and I love it. Let's see. What other kind of energies do we have at work here? We've got the kinetic energies. Now we need to look at potential energies. The first one that should hopefully be obvious is the potential energy for the spring. So we'll have U spring graph can equal G curve. Color equals color dot. What's the color of our spring? I don't think I actually specified one. Let's make that one blue. How about that? We'll give it the label spring PE for spring potential energy. All right, let me copy this name so I don't have to remember it. And then down here, we'll do this backwards this time so I remember to put this in. Let's call the variable spring underscore U. There we go, just to be consistent. Okay, now spring U going to equal potential energy for spring is 1/2 times the spring's stiffness. Where do we have the spring stiffness stored? That is spring.ks times the stretch in the spring squared. Now I've already got a calculation of the spring stretch here. Copy and paste. And they just need to square that. It's a formula that's suspiciously similar to the kinetic energy formula. 1/2 a thing about the particle times a thing about its motion squared. 1/2 a thing about the particle or the object times a thing about its motion squared. That's suspiciously similar, and actually there's a reason for that in conservation of energy. Okay, cool. So let's click run on this. Cool. So our potential energy is increasing then decreasing. Yeah, so basically as these two get closer or farther apart, this thing is going to change. So it's going to vary as these two vary. It's not varying as much because, again, we've got a pretty tight spring here. It's not... it's not moving in and out very much. Primarily, these guys are rotating around each other. Yeah, this thing obeys. Actually, that's a pretty nice cosine curve, which I guess makes sense because no matter what's going on with these two rotating around each other, this spring, their relative velocity is still going to be a simple harmonic oscillator. So this should be a nice simple cosine. I say that if it had come out complicated, I would have come up with some other explanation for it. But that's not the only kind of potential energy we have. We also have the gravitational potential energy of these things falling down. So we've got U graph can equal G curve. Let's call this one color equals color dot. Let's make this one black. And we'll put label equals gravitational PE. Cool. Copy, U graph. Paste uGrav dot plot t comma grav underscore u, we'll call it. And now I need to get the gravitational potential energy. So each one of these atoms contributes to the gravitational potential energy because they each need a mass times the gravitational field times their height. They've got different masses, different heights, so we need to calculate it separately. So let's start with the red one. So we'll have red dot mass times grav. I think that's what I call the gravitational field. Yeah, grav up here. Times red.pos.y. And I could measure this relative to 0 or whatever the bottom value is here, but it really doesn't matter. You get to pick where y equals 0 is for gravitational potential energy, so you can always just put in the y coordinate there. That's for this form of gravitational potential energy. For the kind out in space, you do have an absolute reference of the objects that you're orbiting around. But for the approximation MGH near the surface of the Earth, you don't have to worry about that. All right. All right, here we go. So this is staying somewhat constant. It's starting to fall down because these guys are going to fall. We'll see in a future video. These guys are going to fall like 9.8 meters per second squared as a whole, right? So their center of mass is going to fall like that. So this is actually tracking very well, like a quadratic, like you would expect it to. And of course, this energy has to go somewhere. And so you see both of these speeding up at this point when this thing really starts to fall down, because ultimately these things need to obey conservation of energy. And so the last kind of energy we need to calculate is the total. So let's just have E graph equal G curve color equals color dot purple. Let's go with color dot purple as the king of all the energies. Let's go with color dot purple. Let's see. So we'll need an E graph dot plot T comma E. What did I? Oh, wait, I haven't given it a name yet. Let's make it E total. So I don't think it'll like a capital E since that's exponentiation. E underscore total. We just need to add up all of these other energies. So red K plus green K plus spring U plus grav U. And now, if we've done this correctly, if all of the physics in here is correct, this purple should be a flat horizontal line. All right, it's looking good so far. Oh, I didn't give that a label. All right, well, while that graph runs, let me give this thing a label. I was so excited about finding purple in the list of colors that we could have. I don't think we're doing pretty well. There's a little bit of variation here. Usually when that happens, we want to decrease the time step. So I'll leave that to you as a take-home problem. But yeah, this is pretty cool. So you have all of these wild energies going on, right? The kinetic energies are just kind of doing whatever the heck they want. Potential energy is sailing downward steadily. Spring potential energy is wobbling a little bit, but they always add up to a constant total up here, which I think is pretty cool. Oh, let's run that again, make sure our label got in there. Okay, there we go. There's our total energy. So yeah, I hope this is helpful to you. I hope this is a good supplement for this chapter in matter and interactions. We'll be working with this code for a few videos. We're going to take a look at how the center of mass behaves of this system. And then we're going to take a look at how we can use this to model a bouncing ball. And then we're going to have a little fun with a bola toss a little bit later. So thank you so much for watching. I will see you next time. Bye-bye.